Hello there. In the last video session we have seen by using the rectangular coordinate system, when the particle is moving in a curvilinear motion, we have found out the resultant velocity as well as the acceleration. Now I am going to be using another coordinate system, that's going to be a normal and tangential coordinate system I am using to find out the velocity as well as the acceleration of these particles. There we can see this is going to be the x, this is the y. So then I have given one abruptly the curvature I have taken over here, that's going to be in this way I have taken, and the particle is going to be existed at initial condition at a certain time at A. After certain duration of the time it reached to the B. Can you see the particle is traveling along the curved path? It is going to be clear. Now we need to find out the certain parameters over here. When the particle is moving from A to B, I am going to be taking, that is a small displacement it has taken, right? So for this one I am going to be taking here and extending these points towards this side, because can you see it is going to be consist of the curvature is there. So then what will happen, throughout the length the radius of the curvature is going to be constant. So then what happened, I am going to be taking towards this side, and similarly I am going to be taking here. When these two are meeting, that's going to give the radius of curvature that I am going to be representing here with the rho. We can represent with rho, or maybe you can take with the r also. So this is going to be, I am going to say the displacement is going to be your del theta. Can you see that is a small displacement it has taken. And similarly what will happen, I am going to be taking here the small displacement means, so I am going to be taking one straight segment I am taking. The distance travelled from A to B, I am going to be say this is your ds, right? So that is going to be your ds distance it has travelled. Now I am going to be taking, by using the normal as well as the tangential coordinate systems, I am going to be draw the further diagrams over here. Can you see, I am going to be taking the tangential velocity of this component. The tangential velocity always it is moving on the tangent to the particular point of the curvature. So then it is traveling in this direction. So this I am going to be say velocity v, that is your tangential component, and it is going to be making an angle of theta. After certain duration it has changed its position from A to B, and then I am going to be taking here another tangent. So I am going to say v plus del v, I am going to be say, because the velocity changed from A to B. When it is moved from A to B, the velocity has got a change v plus del v. And then I am going to be say this is going to be theta plus del theta. Whatever the increment is going to be there, so that I have mentioned over here. Clear? So then once it is going to be in this position, I am going to be taking here the two components. One is going to be tangential component, another one is going to be your normal component. So then this is going to be moving in this direction. So it is going to be making del theta. Alright. So when I am going to be resolving this force, one is going to be normal to this point. What that means, in the tangential direction, one is going to be a normal to that point. So then I am going to be say this is going to be v plus del v cos del theta. Right. And similarly, and another component I am going to be taking towards this side. So this is going to be v plus del v sin del theta. There we can see, by using these components we are going to be calculating the velocity in the normal direction, the velocity in the tangential directions we are going to be calculating. So now we are finding the tangential velocity vt. So how to calculate here the distance moved along tangential direction divided by, so the velocity is going to be, it is going to be your time. The distance travelled along the tangential direction divided by, we are going to say the time we are taking. So here the distance travelled along the tangential direction, which one is going to be the tangential direction in this case? Can I take it here A, B as well as the C 3 points I am going to be taking. For the further continuation, I am going to be taking, this is going to be your A, this is the point B, and this is going to be in this direction, this is going to be E. So this is the point C we are going to be say, and say this is going to be the del theta I am going to be calling. Alright, when the del theta is there. So this distance A to B I am going to be say, this is going to be your del S I am going to be say. Opposite to this one I am going to say del S sine del theta, and this one is going to say del S cos del theta I can say. Can you see, these two are going to be the distance traveled. One is going to be tangential to this one is going to be normal to this point. So for this one I am going to be taking, because the small distance I have taken, the limit del tends to 0, I am taking del S, because the tangential directions I will need to take it. This is your tangential direction, that's going to be del S cos del theta by del T. So as we know that the further simplifications if I am going to be do, so then what will happen, cos del theta will going to be, what is the, therefore cos del theta is going to be the very small, that's going to be 1 we are going to be getting, because del theta is going to be the very small. So if I am going to be substituting in this equation, and this is also the time tends to 0, so finally the Vt is equal to the limits del tends to 0 del S by del T I am going to be getting, and further I am going to be writing ds by dt I will get it. So Vt is equal to ds by dt formula we will get it. So this is going to be your the velocity along the tangential direction of your the particle. So now we are finding the normal velocity of that particle. So that is equal to the distance traveled normally to the distance traveled in normal direction, divided by time interval. So in this case, which is going to be the distance traveled from this one, that's going to be del S sine theta is going to be your normal component. So that's going to be Vn is equal to limits del tends to 0 del S sine del theta divided by del theta. As we know, del theta is going to be the very small. It means that it tends to 0, then sine 0 is equal to 0 we are going to get. So that's I am going to be getting sine del theta is equal to del theta only I am going to be writing. The same I am going to be writing over here. So the Vn is equal to limits del t tends to 0. This del S I am writing as it is, and del theta divided by del theta. So in this case, this is a very small component. The product of this one is going to be the very small component. So then Vn is equal to 0 I am getting. So we got the velocity. So in this case, Vt is equal to ds by dt. That is, the tangential velocity is equal to ds by dt. And similarly, the normal velocity is equal to 0. I got it. In the normal direction, the velocity of the particle is going to be 0. Once we have calculated the tangential velocity, and we need to calculate the tangential acceleration. As we know, the tangential acceleration is equal to the rate of change of velocity with respect to the time we are going to be taking. In this case, the rate of change of the velocity, tangential velocity by time we are going to be taking. The change in tangential velocity by time interval we are going to be taking. Can you see, at this point the tangential velocity is going to be the v, but when it is reached to the point b, it comes to the v plus del v. When I am going to be resolving to the two components, one is going to be v plus del v cos del theta. Can you see, this velocity and this is going to be the matching over here. That means this is going to be your velocity, tangential velocity component. So the same, the limits del tends to 0, I am going to be taking v plus del v cos del V cos del theta minus V I am going to be taking here divided by del T I have. So in this case, this is the equations I got it, right? So this is equation del V. So if I am going to be simplifying this equation, then what will happen? Cos del theta is equal to 1 because it is reaching to the very small amount. So then cos 0 is equal to 1 we are getting. Further simplification from this one I am writing here. So limit del equal to 0 V plus del V minus V by del T. So in this case what will happen? The V will going to be cancelled out. So then del V by del T only we are going to be getting here. That's going to be limits del tends to 0 del V by del T. And further I am going to be writing dV by dt. So here the tangential acceleration of that particle at point B is equal to dV by dt. I got it. So can you see the tangential velocity is ds by dt, at the same time the tangential acceleration is equal to dV by dt. So once we calculated the tangential acceleration, now I am going to be calculating the normal acceleration of that particle at B, suppose. That is equal to change in normal velocity by time. There you can see this V plus del V cos del theta we do have taken that as a tangential component. Now that opposite to this one is normally to this one, V plus del V sin del theta is going to be your change in velocity. So that's I am taking limits del t tends to 0, that's V plus del V sin del theta minus V divided by del theta we are going to, because we need to take it the change in velocity. So further simplification, sin del theta is equal to small del theta only we are going to be considering. So if I am going to be substituting in this equation, limit del t tends to 0. So in this case what will happen? This component will become del theta. So and further simplification of this one, V plus del V del theta minus V by del T. So can you do the further simplification of this one? If I am going to do, I will get it that equation in this way. Limit del t tends to 0 V del theta plus del V del theta minus V by del theta. So in this case del V as well as the del theta is going to become, after the product of these two is a very small component. So that we are going to be taking is going to be nullified. So further equations. So in this case what is the V here? This is going to be your normal velocity. Normal velocity at the point A is equal to, we got the 0. So that means this is going to be the 0 and this is also going to be the 0 I am taking. And further simplification I am going to be writing over here. So here is going to be the simplification. That's going to be an is equal to limits del tends to 0 V del theta by del t, and by when it is approaching B d theta by dt. I am going to be simplifying this equation. That's an is equal to V into d theta by ds by dt. So can you see here, when I am going to be simplifying this equation, I am going to be getting ds by dt is going to be your the velocity component, right? So that I am going to be getting here is the V. So this product is going to be the V. So that's going to be V square. Can you see d theta by ds is going to be your rho. Can you see here ds, rho and del theta. So from this one the del theta, if I am going to be taking, so from that simplification for your understanding here, I am going to be taking the del theta is equal to opposite by this one ds by rho if I am going to be taking, and this is going to be rho is equal to ds by d theta. So here ds by d theta by ds is there, and that I am going to be getting here ds by d theta, if I am going to be taking v square by rho, that is going to be your normal acceleration of your component, of your particle. An is equal to v square by rho. Can you see? Either rho or we can say that is the r also we can say. This way we are going to be calculating the normal acceleration. Now we are trying to find out velocity with respect to this point of that particle. Right? As we know, this is going to be the point where this is the point B. A, this is going to be the A, and this is going to be your ds. It is making the del theta. This is the rho. Right? If I am going to be taking ds is equal to del theta is equal to ds by rho I am getting. ds is equal to rho into d theta if I am going to be considering. So then I am going to be taking the velocity of this part. So the velocity with respect to this point, so that means from this one, the velocity v is equal to, what is the formula we do have? That's going to be changing the displacement by time factor I am going to be taking. The ds I am going to be substituting rho into d theta by dt I am going to be taking here. So there we can see, so this is going to be rho into d theta by dt. So this is going to be the rate of change of angular displacement with respect to the time. We are going to be say angular velocity. So the v is equal to rho into omega I am going to be taking. The rho is nothing but here, the omega is nothing but the rate of change of angular displacement with respect to the time. We can say that is going to be your angular velocity. So v is equal to r. We can say this, the rho also we can say that's going to be r into omega also we can write it. So either you can take r into omega or v is equal to rho into omega also we can take it. This way we are going to be calculating the velocity at the different positions. One is at A, one is at B, another at going to be the center of the radius of curvature. So I hope you are able to understand how to take it, the normal and tangential coordinate systems, right? If you feel any difficulty, so please put in your comment section so that I can reach you by making another video where you are going to be feeling the little difficulty. I hope you people are going to be following the series of video lectures so that for better understanding it is going to be helpful to you. So thank you. Please subscribe to my channel. Thank you.